In the annals of scientific thought, 1916 marks a pivotal year, witnessing the publication of Gilbert Newton-Lewis' seminal work, The Atom and the Molecule. This treatise emerged from an environment where the very architecture of chemical bonds remained shrouded in mystery. Existing models, particularly atom models, proved inadequate in explaining the observed diversity and behavior of molecules. Lewis sought to reconcile these disparities, aiming for a more intuitive model capable of predicting molecular properties and reactivity with greater accuracy. At the heart of Lewis' contribution lies a profound shift in perspective. Rather than viewing atoms as immutable spheres, he envisioned them as entities driven to achieve stable electron configurations, often mirroring those of the noble gases. This drive, he posited, underlies the formation of chemical bonds. Preceding Lewis, Richard Abegg's work on valence offered a crucial stepping stone, Abegg's rule, suggesting that the sum of an element's positive and negative valence is often equals 8, hinted at an underlying pattern in chemical bonding. Lewis seized upon this notion, developing it into the no famous octet rule. Lewis' innovations extended beyond mere observation. His work gave birth to 3 groundbreaking concepts. First, the cubical atom, a bold yet elegant geometrical model where electrons occupied the corners of a cube surrounding the atomic nucleus. This model, while ultimately superseded by quantum mechanics, provided a visualizable framework for understanding electron arrangements in simple molecules. Consider methane. The cubical atom model envisioned carbon at the center of a cube, with each of its 4 valence electrons occupying a corner. Hydrogen atoms, each contributing an electron, would then attach at these corners, completing the carbons. Second, and perhaps most enduring, is the octet rule. Lewis proposed that atoms tend to gain, lose, or, crucially, share electrons to achieve a complete outer shell of 8 electrons, mimicking a stable configuration of noble gases. This principle offered a powerful predictive tool for understanding chemical reactivity and molecular stability. For instance, the formation of sodium chloride becomes immediately comprehensible. Sodium donates an electron to chlorine, each attaining an octet and forming a stable ionic bond. Third, the concept of the shared electron pair, or covalent bond, revolutionized the understanding of chemical bonding. Lewis argued that atoms could achieve stable octets by sharing pairs of electrons, effectively creating a glue that held atoms together. This explained the formation of countless molecules where atoms exhibited a sharing relationship rather than a complete transfer of electrons. A prime example is the hydrogen molecule, where 2 hydrogen atoms share a pair of electrons, each effectively achieving the stable electron configuration of helium. The initial reception of Lewis' ideas was a mixture of enthusiasm and skepticism. His model offered compelling explanations for many observed phenomena. The scientific community appreciated the model's conceptual simplicity and visual appeal. As demonstrated by the cubical atom, it provided a tangible way to visualize electron arrangements and chemical bonding, which aided in understanding molecular structures. However, the cubical atom and the octet rule represented a marked departure from established classical physics, raising questions about their theoretical underpinnings. One source of skepticism stemmed from the model's reliance on empirical observations rather than rigorous theoretical derivations. While the cubical atom and the octet rule yielded successful predictions for many molecules, they appeared somewhat arbitrary. The scientific community needed to understand how these rules emerged from fundamental physical principles. Despite the initial reservations, Lewis' work sparked a new wave of research. His ideas provided a framework for understanding the structure and properties of molecules and stimulated theoretical and experimental investigations. The conceptual simplicity and visual nature of the cubical atom made it a powerful tool to explain chemical bonding, even though it did not fully align with evolving quantum mechanics. This essay will delve into the specifics of Lewis' model, tracing its immediate impact on the field of chemistry and examining its long-term legacy. The essay will further discuss how Irving Langmuir's subsequent work on Lewis theory, including concepts like isoelectronic species, shaped our modern understanding of atomic structure. Finally, it will explore the refinements and modifications that shaped our understanding of the chemical bond into its modern, quantum mechanical interpretation. It will explore the limitations of the octet rule and the subsequent exceptions to it. In doing so, it will highlight the enduring contributions of the atom and the molecule in laying the foundations for contemporary chemical theory. Gilbert Newton-Lewis, in his seminal 1916 work The Atom and the Molecule, presented a revolutionary model of chemical bonding that, while predating the full development of quantum mechanics, profoundly shaped our understanding of molecular structure. At its heart lay the concept of the cubical atom, an ingenious geometric representation of electron arrangement. Lewis envisioned the atom's valence electrons positioned at the 8 corners of a cube, providing a visual framework for understanding how atoms interact to form molecules. This cubical model, although ultimately superseded by quantum mechanics, offered an intuitive explanation for the periodic properties of elements and the formation of chemical compounds. Specifically, the cubical atom model illustrated how elements tended to gain, lose, or share electrons to achieve a stable octet configuration, reminiscent of the noble gases. For example, in sodium chloride, sodium, with one valence electron, could readily donate it to chlorine, which possessed 7. This transfer resulted in both ions attaining a full octet, leading to a stable ionic bond. Similarly, in the case of methane, carbon, with 4 valence electrons, could share each electron with 4 hydrogen atoms, thus forming 4 covalent bonds, so that all atoms achieved a full valence shell. These geometric representations brought clarity to chemical interactions. The concept of the shared electron pair, or covalent bond, was a key contribution of Lewis' model. In molecules such as hydrogen gas, 2 hydrogen atoms shared 2 electrons, with each atom contributing 1. This sharing created a stable, electron-rich environment that held the atoms together. Lewis' representation of this sharing, through graphical structures that later evolved into Lewis dot diagrams, provided a simple yet effective way to visualize covalent bonds, predict molecular structures, and understand chemical reactivity. Irving Langmuir significantly expanded upon Lewis' ideas, coining the term covalence and developing the concept of isoelectronic species. Isoelectronic species are atoms, ions, or molecules that possess the identical number of electrons and, consequently, similar electronic structures. Langmuir's meticulous work provided additional validation for Lewis' theory, deepening its impact on the scientific community. Subsequent experimental evidence, including spectroscopic data and measurements of molecular properties, continued to support Lewis' model and its refinements. Despite its considerable successes, the Lewis model, particularly the octet rule, possessed limitations. Molecules with expanded octets, such as sulfur hexafluoride, where sulfur is bonded to 6 fluorine atoms exceeding the standard octet configuration, challenged the theory's universality. Furthermore, electron-deficient compounds, such as boron trifluoride, exhibited stability despite boron possessing only 6 valence electrons, providing another exception to the generally accepted octet rule. These exceptions highlighted the necessity for a more nuanced understanding of chemical bonding that could account for these deviations. As quantum mechanics matured, valence bond theory and molecular orbital theory emerged as more sophisticated methodologies for describing chemical bonds. Linus Pauling, by applying quantum mechanics to Lewis' original concepts, developed valence bond theory in the 1930s. Valence bond theory explains chemical bonding through the overlap of atomic orbitals to form shared electron pairs, essentially quantifying Lewis' descriptive covalent bond. Further refinement occurred with the development of molecular orbital theory, which views electrons as existing in molecular orbitals that extend over the entire molecule, rather than being confined to individual bonds. These quantum, mechanical approaches refined Lewis' initial ideas, eventually resolving many of the limitations of the octet rule and providing a more accurate portrayal of the electron distribution in molecules. In conclusion, the atom and the molecule stands as a monumental achievement in the history of chemistry, marking a transition from classical to quantum mechanical descriptions of the chemical bond. While Lewis' cubic atom and octet rule were eventually superseded by more accurate quantum mechanical models, his intuitive model provided the bedrock for our current understanding of chemical bonding. His emphasis on the shared electron pair and his innovative use of visual representations offered chemists an invaluable toolkit for understanding and predicting molecular behavior. Gilbert Newton Lewis' work thus remains a testament to the power of insightful, conceptually driven science. His contribution continues shaping modern chemistry,